Okay, so we're gonna start today. Earlier, we just discussed the due dates and stuff. So I will email after class today. And today we're gonna start a new chapter, which is Gibbs sampler and MCMC. So I posted the slides on Moodle, so you can get that. And let me bring it up here. So, all right, so this unit chapter is about, well, what if you encounter the situation that posterior distribution is not available? So we're gonna use the example of the normal sampling that we covered for the situation where you have the log transform total expenditure. And then we're gonna start from there, realizing that, well, what if both parameters are unknown? And so we're going to start with that. And then when both are unknown, you will have to figure out ways to do prior distribution, derive the posterior, et cetera, et cetera. So we're going to see how you can design a Gibbs sampler where both of them are unknown to solve that particular problem. But Gibbs sampler and Markov chain multicolor can go beyond just the normal example that we did. Like we will repeat. So later you will see that there are other situations that Gibbs sampler will be helpful. But we start with the normal sampling context, because we're, I hope, still pretty fresh about with it, so it will be easier to cover. So we're still going to start the example with the expenditures in the consumer expenditure surveys. And now you see that the second topic will be prior and posterior distribution for mean and standard deviation. Okay, we're going to assume that both of them to be unknown, and they're going to work out the Bayesian inference for it. And later we're going to use this JAX, just another Gibbs sampler. It's a software that can help us to solve the MCMC. And then in the end, we're going to talk about MCMC diagnostics. Okay. So example, again, the data set is csample1.csv. It's from on Moodle. And then this is the case that we looked at. Remember, just look at the raw format of this data, and we realized that's extremely few, right? So that's the case that we took the log, and then we start to work with something more symmetric. And then that was the case that we assumed that we're going to use a normal sampling model, right? We fix the mean, or we fix the standard deviation and work with the other one being unknown. And then we worked out the conjugate prior cases for both of them. So before we get there, again, the normal distribution again, this is two parameters, mean and standard deviation. This is the PDF. And then this is different normals that we looked at before. But most importantly, I would say, when you have each response independently and identically distributed, this is what we use IID, right? And then the key, as you have seen in the derivation exercise that we did before, it's very important to know how to write the joint likelihood. Okay, so we've seen this, right? For the case where mu is unknown, sigma is known, or the other way around, regardless, you have to work with equation 1. Okay, that will be the joint likelihood. So super important to know how to come to this point, and of course, later how to further derive it to come to the posterior distribution. Okay, so this still stays. We're still going to work with it. And so remember, whenever we're trying to do Bayesian inference, the step 1 is thinking about the prior distribution. Okay, so if we're going to do the data model or sampling density for the IID normals like we used to do, and we know that there are two parameters, mu and sigma, so the likelihood is in terms of both unknown parameters. If you don't know anything about them, right? Like if both mu and sigma are unknown, then we write likelihood is mu and sigma, both of them, to start with. And then that means you will need a joint prior distribution, and that will go to a joint posterior distribution. Okay, so this is the case that if both of them are unknown, then the likelihood should be in terms of both unknown parameters. The prior distribution now becomes a joint prior. We're going to learn how to give joint prior in this case. And then, of course, in the end, we're trying to come to a joint posterior. And so now everything is unknown, so you put everything together. And we use joint likelihood, joint prior, and then joint posterior. So this is the setup I think we're familiar with. And what we did before, this is the case that sigma is known, mu is unknown, so we cover the normal conjugate prior. So I'm just showing this again. It's exactly the same as what we did before, but just to give you a review. And pay attention that for the ease of doing derivation and later computation, we work with precision. Okay, so precision is 1 over sigma squared. So you work with that, and you come to equation 7. So that's the conjugate normal prior. Last time when we were going through the gamma cosine, I think there's this question about conjugacy or conjugate prior. So in this case, the prior distribution we give to mu is a normal, mu 0, sigma 0, and then you come to its posterior to be another normal. But they're both from the normal family distribution, so they're conjugate. So that's what we mean by conjugate prior. So this is for the mu is unknown. And for the sigma is unknown, again, we use the gamma conjugate prior for the precision 1 over sigma squared. So start with gamma alpha beta, and then you're going to come to a gamma with 2 new parameters. Okay, so we looked at, I think, for both this case and the previous mu unknown case, we looked at how, like say, especially the previous case, the posterior mean is the weighted average of the prior mean and the sample mean, all that, and how the sample size is affecting the situation. So all of those are important lessons in terms of Bayesian inference overall, and we can see interesting results for those simplified cases. Okay, so this is what we did before. And now the task is, what if both of mu and sigma is unknown? So if you're working with lab 2, you might notice that, well, lab 2, I think, is when mu is unknown, right? Sigma is known, so we have to make assumption what mu or what sigma is. I give you a number to you, but that might not be a good. So first of all, how to came up with that? I think I was just using the sample standard deviation to keep things simple, so that might not be a good thing to do. And second of all, who knows whether the sigma should be fixed or should be random? Okay, so if you want to give the model enough flexibility, you might just let it be random as well. So this is the motivation of why you want to have both parameters unknown, and then how to carry out the remaining steps of the Bayesian inference is the focus today. So let's go back to the case. Mu and sigma are unknown. I'm throwing out things here. Don't worry if you are not too sure why this is the case for now. But we're gonna decipher it step by step. So let's think about a joint prior distribution in terms of equation 11. So you see that I break out the joint prior mu and sigma to be pi 1 mu and pi 2 sigma. Okay? So essentially, I'm saying that the two, the two parameters, I give independent priors to them. Okay? So only if you think they're independent, or I should say the joint distribution is the product of two marginal distributions in this case. Okay, so the key when I'm giving a prior in this way is I'm assuming that they're independent. There are other ways you can give priors, dependent. But to start simple, let's think about the simplest case. So you assume they're independent. So we're going to work with pi 1 and pi 2 separately. And what I'm proposing here, as you can see in equation 12 and 13, you might find this pretty familiar. This is what we used to do when one of them is fixed, the other one is random, right? So pretty much, this is the first prior, pi 1, if we follow the notation equation 1. So this is the prior, normal mu 0, sigma 0 is the prior that we give for mu. And then this is pi 2, that it's the gamma prior, gamma alpha beta that we give to 1 over sigma squared. Okay? So nothing changed much, but we do start to assume that both of them are unknown, both of them are random. We're giving two prior distributions, one to each of them, and specifically in equation 11, we're assuming that they're independent, so we can break the joint into the product of the margin. So this, again, goes back to the probability review that we did before and your other coursework in the past. So this is a key assumption that we're making here. And again, we're making this assumption just to make our life easier. So you will see that if we're going to use equation 11 through 13, that we're using dependent priors, we're using these two particular priors, normal and gamma, we can come to something what we call full conditional posterior distribution. Okay, so Equation 14 and 15, if you look at it, it's exactly the same as what we did before. Okay, so I'm going to give you some time to think about it. Especially, can you convince yourself that without doing all of the derivation again, that this is true? Notice that what we are doing here is that the full conditional posterior distribution. So we only covered posterior distribution before, right? That's just like, say, for an unknown parameter, we're looking at, say, mu, then we're looking at the conditional distribution of mu given the data. Okay. Now we introduce a new definition called full conditional posterior distribution. That is when you have more than one parameter, in this case, mu and sigma. Okay. And we define the full conditional posterior distribution as for each parameter, I'm looking at it given everything else. Okay. So you can think about it as everything else. Everything else in this case not only includes the data, but also all of the other unknown parameters. Okay, so that's why we call it a full conditional posterior distribution. Sometimes when you have so many parameters and then it's so complicated to write it, you will see that later in the exercise and stuff. You might just write mu given and then like a hyphen just to represent everything else. Okay, but for now, we're only working with y1 through yn and also one other parameter, so we just write out everything. But in short, the full conditional posterior distribution by definition is for each parameter, you're looking at its conditional distribution given everything else. Okay, so that's why for mu, you're given y1 through yn and phi, which is the other unknown parameter, right? And then for 1 over sigma squared, which is phi, it's given the data and the extra parameter mu here. Okay. So this is a definition. And I want you to think about it.
Excuse me.
Yes, go ahead.
Here we're assuming a normal likelihood again, right?
Right, it's still a normal likelihood. Yeah, so it was from, I guess, previous slide. So we're still assuming, yeah, y1 through yn, there, IID, normal, with mu and sigma. Does that answer the question?
Yes.
Yeah.
I have a different question also on this. So when we're specifying our prior beliefs, how many things do we have to specify? So it's mu 0, sigma 0, and also alpha and beta, or is it just we use the sigma 0 as our belief?
Yeah. Right,
Okay.
Great question. So before we were covering this, when only one parameter is known, or unknown, I should say for mu, then we're going to give values for mu 0 and sigma 0, right? So in lab 2, if you're working on it, I think I gave 5 to mu 0 and 1 to sigma 0, right? And then that was the case in lab 2. That was the case that we assume that sigma is known. We don't even give like a prior to it, let alone this alpha and beta in this case, okay? But now we're assuming both of them are known, so we're giving 2 independent priors. So when you try to work it out, like right now we're at the stage of thinking about the derivation, but later if you want to implement it, like what Jorge was asking, I think you would give values for mu 0, sigma 0, alpha, and beta. In all of them, because now mu 0 and sigma 0, they are what we call hyperparameters. So they are parameters for the distribution of parameters. So they are called hyperparameters. So you would need mu 0 and sigma 0 for mu, and then gamma, alpha, and beta for 1 over sigma squared. And so later you will see, if we're going to code the Gibbs sampler, which is how we can do the computation later, we'll have to fit in the 4 values. Okay, we have to give some values to them. I think I will be doing mu 0 to be 5, sigma 0 to be 1, and alpha beta to be 1, both of them to be 1 to start with. Okay, but I think linking to Jorge's question, this is just, well, now I'm working with 2 independent priors, and I need to give exact priors to them, so we have to fit in 4 values. Okay, mu 0, sigma 0, beta, and alpha. Does that answer the question?
Yes, thank you. But I actually, so isn't the fact that when we choose our sigma 0, doesn't that sort of already pick our alpha and beta, or are those 2 not related?
Yeah, those two are not related, and this is
Okay.
a great question. So, okay, so let me repeat the question. So, yeah, so the thing is, there are multiple normals going on, and we saw it before, right? Like, so overall, the likelihood function is a normal, okay? That's for sure. And then with mu, because we want to work with conjugate prior, so we realize that for the unknown mean, we're gonna give a normal prior as well. So this sigma 0 is on mu. It's not on sigma. Sigma is separate. So I'm guessing how his question is linking to this point that, well, if I'm choosing like a value for sigma, am I duplicating what I'm doing with sigma, a value for sigma 0? Am I doing anything duplicating for sigma? So again, there are two different things, okay? So later in next unit, we're gonna learn about hierarchical modeling, but for now, just think about, like, say, how we can express this. So we have y1. It's not necessary for the simple case like this, but it probably can help us to think about how the data or how their relationships are. So for y1 through yn, we know that it will have the effect of mu, right? And then it will also have the effect of sigma. And so I'm using this kind of graphical representation that I know for mu, for each of the observations, it comes from this normal distribution, right? So there are two factors, two parameters, mu and sigma, right? So I can write them separately. And then further, I know that mu is being affected by mu 0 and sigma 0, right? And then further, I can express my my sigma to be affected by alpha and beta. So that's why you can see that sigma 0 and sigma, they're separate. Sigma is the standard deviation for the likelihood function, and sigma 0 is the standard deviation for the normal prior for the mean. So that's why, in order to give a prior for mu, you have to give values of mu 0 and sigma 0. And then in order to give a prior for sigma, you will have to support values of alpha and beta. So I think Jorge's question is great. And this, again, I think relates to the fact that we have the likelihood to be normal, and then the prior, one of the priors is normal as well. And so, and then of course for sigma squared, 1 over sigma squared is gamma, so it's sort of like separate, so it's less confusing. But I think the normal conjugacy that we covered before and now appearing again is the important definition to cover and then keep in mind.
Thank you. That answers exactly my question.
Yeah.
Thank you.
Great. Thank you for letting me know before I ask you. And all right, so okay, so keep this in mind. And now you see equation 14 and 15. I was saying that they look exactly the same as if we are assuming one of the parameters is unknown. Is known, right? So, so in fact, to derive 14 and 15, you can start from scratch. You can write out the likelihood function, you can write out the prior and all that, and then you will be able to come to the same point. So we can do that, but before we do that, I want you to maybe convince yourself that even before or even without doing it, by the definition of full conditional posterior distribution, that is, if I'm working with mu, I'm assuming that phi is known. That is, if I'm working with phi or 1 over sigma squared, I'm assuming that mu is known. So can you come to the conclusion of full conditional posterior distributions of 14 and 15 based on the definition that we just covered? Or not? Okay, so take a couple of minutes, talk with your neighbor, and I will show you the steps. I mean, we can work together of the steps of deriving it like accurately. But just based on the definition, what do you think? Can you convince yourself that it is true? Okay, so if we don't derive it, can you convince yourself that we will come to equations 14 and 15? And why? What? Without derivation, can we convince ourselves that equation 14 will just be the actual full conditional posterior distribution? It looks exactly as before. Does that make sense to you? Why?
So if mu and sigma or position in this case are independent, then the probability for mu is the same as probability of mu given sigma because sigma doesn't have any effect on mu.
Yeah, so we start with joint prior, and then we use independent two priors like this. So if we keep in mind the definition of full conditional posterior distribution, that is for mu, I'm conditioning on everything else, including the data and the other parameters. So if that's the definition, then soon we're going to start the derivation exercise. But pretty much, if you want to find the full conditional posterior distribution for mu, you're going to collect in the likelihood everything about mu, right? And in the prior, everything about mu. Everything about sigma or phi doesn't matter. Okay? So that is why if we have the same likelihood as before, right? Even though now we have two priors, one for mu, one for 1 over sigma squared, but sigma squared or phi or sigma itself, we're assuming that it's known when we're deriving the full conditional posterior distribution, then the prior reduces to pi 1 mu, right? It's only going to matter what mu relates to. So that's why from the likelihood, we're still going to have the same thing as before. From the prior, we're only going to have things from this normal mu 0, sigma 0, and that resembles what we did before. And that's why you can come to equation 14 directly. Okay. Similarly, if you're going to just focus on the full conditional posterior distribution for phi or 1 over sigma squared, then from the likelihood, you only collect things about sigma squared or phi, right? And then from its prior, equation 12 doesn't matter anymore because it's about mu, and mu is given in this case. As you can see, we always put it after the conditional sign. So the prior contribution only comes from equation 13, and that's the same as before. Okay? So that's why you see that equation 14 and 15 are exactly the same as before, but we now define them differently. Okay? In the past, when we assume that phi is known to start with, then we call equation 14 as just posterior distribution. And it's just for mu. Mu is the only unknown. Okay? Now we assume that both of them are unknown, and we come to this full conditional posterior distribution that is for a particular parameter given everything else. So equation 14 becomes the full conditional posterior distribution for mu. Okay? And equation 15 becomes the full conditional posterior distribution for phi or 1 over sigma squared. So notice the difference. In the past, we just worked with posterior distribution because by definition, posterior is the unknown parameter given the data, right? But now we have two parameters. What are we going to do? We're going to assume that the other parameter is known, in this case, whenever we're deriving equation 14 and 15. But for both of the parameters, they're unknown to start with. Okay? It's only when we're defining full conditional posterior distribution and deriving them, we're assuming that the other one is known for now. Okay, but both of them are unknown to start with. All right, so keep those in mind, and I guess we'll just be good practice to make sure that we all know how to do any kind of joint posterior derivation. So remember, we have y1 through yn, ARIID, normal, mu sigma. Okay, that's the likelihood. So you're going to figure out what you're going to do. And then for prior, mu, and sigma, we give them independent prior, right? So that means, let me actually write it. That would be easier to do. So we give mu, normal, mu 0, and sigma 0. And we give 1 over sigma squared to be gamma, alpha and beta. Okay. So notice that above this is the likelihood. Below this is the prior. But we're giving two independent priors. So that's why you can write them on different line. And then the goal is to get mu and 1 over sigma, the joint posterior. Okay. So this is what we call joint posterior. And what we're doing right now is, instead of working with the joint posterior directly, we'll break it into two parts. Both of them are full conditional posterior distribution. Okay. So you will have to deal with mu given y1, 2yn, and phi, okay, which is 1 over sigma squared. So you need to work with piece 1. You also need to work with piece 2, which is 1 over sigma squared given the data as well as the mean. So joint posterior is when mu and sigma squared or 1 over sigma are considered together. But then the new definition, full conditional posterior distribution is exclusively defined to be looking at one parameter at a time and given everything else. Okay, so I'm just going to give you, I guess, a couple of minutes just to try it out. Again, like what we were talking about earlier, you can pretty much already see the results, right? See the resemblance to what we covered before. But I want you just to try it out in a sense that, well, for the full conditional for mu, what we do is it should be the likelihood function about mu times the prior, which is pi 1 when we're working with mu, right? And then for the full conditional posterior distribution for 1 over sigma squared, then it's going to be 1, the likelihood in terms of this, and then the prior. Okay. So if I write it this way, you can see its resemblance to what we covered in the previous chapter, right? But now we're talking about different things. They are called full conditional posterior. So the derivation will be very similar as before. I don't think we're going to cover it step by step in class, but I want to give you a couple of minutes just to sort it through the idea, and then maybe just try out a list to practice writing out your likelihood function in terms of mu, and then its prior, and also the likelihood function in terms of 1 over sigma and its own prior. Okay. The rest will follow what we did before, but this is a new setting that we have two unknowns. So we come from joint posterior into the full conditional posterior distribution, and each of the two derivations resembles what we did before. Okay. So take some time, think this through, see the difference and similarities as before. Now walk around to answer more questions. All right. So do you think you will be able to derive it all in the logic here? So the key whenever we're doing more than one parameter is that we're going to assume the other one should be known when we're deriving the full conditional posterior. That's by definition, because full conditional, then you're conditioning on everything else. So those, anything else, including the data and the other, or in this case, it's one other parameter, but in later cases, you will see more than one parameter. They all go into the conditional side, and then you can assume that to be constant. So that's why you never need to worry about that. Okay. And that's why, so if we go back here, that's why in this situation, without even deriving 14 and 15, based on what we did before, because we're giving exactly the same prior distribution, right? 13, equation 12 for mu, and the equation 13 for 1 over sigma squared. So you're going to come to 14 and 15, okay, based on what we did before. Okay. But just keep in mind, these are two different terminologies. Right now it's full conditional, previously just the posterior. Okay, and full conditional posterior distribution going to be super handy now and useful because typically you're going to work with models with more than one parameter. Okay. And if we can derive its full conditional posterior distribution, we can design what we call Gibbs sampler to help us do the computation. Okay. So now we're going to come to the details of how to, based on equations 14 and 15, how we can do the actual computation. All right, so the sampling scheme is what we call Gibbs sampler. Gibbs sampler is a pretty big, it includes many other variations. So in this case, Gibbs sampler can be used because both of the two full conditional posterior distributions are exact. That we know one of them is normal, the other one is gamma. Okay, so whenever you have all of your full conditional posterior distributions are known distributions, then you are able to use what we call Gibbs sampler. Okay. So how are you going to do it? So you can start with initial values for the parameters. So you see the notation that we use. I try to use the upper script of parentheses and in that indicating the iteration. So initial values would just be like 0 at iteration 0. Okay, you give some initial values for mu and p in this case. And then you're going to generate a large number of simulations. We use capital S again to indicate how many iterations we do. So for each small s in 1 through s, we're going to generate the following sequence of the full conditional posterior distribution. So what we do is, so you start with initial value, right? But then at a particular iteration, what you do for mu, you're going to generate it from, this is, I would say, I think equation 14 that we had before. Okay? I didn't write it out here, it's too long, but that is the normal full conditional posterior distribution. Okay? And then for phi, or 1 over sigma squared, whichever you do, it's going to be drawn from its own full conditional posterior distribution. So I think it's corresponding to equation 15. So you do that, and then you come to, so we use theta to represent the collection of the two parameters. So you can get, at this particular iteration S, you can get mu S and phi S. Okay. So one thing to know here is that if you look at the upscript, like in terms of iteration, you see that for mu S, we're using phi S minus 1, because you have to use it from the previous iteration. But as soon as you update mu, you can use the current mu for generating current phi. Okay? So this is an iterative process. And I start with mu 0, phi 0, or even just starting with mu 0. Even if you don't have phi 0, you can generate phi 0 from its full conditional posterior distribution. And you do it iteratively. Each iteration, you are doing mu first, and then phi second. So intuitively, when I go to my next iteration, my mu s plus 1, right, will be coming from mu given phi. Now it's going to be s, right, because I already have my iteration s of phi here, and given the data. And then I can do my phi s plus 1. Now it's going to be phi given mu s plus 1. Okay. So again, you do it iteratively. When one parameter is updated, you're going to use the most current version for the next parameter.
Yeah. Is there a reason that we do like mu first and then update?
No. Yeah, there's no reason. So you will see that the script I'm gonna share with you soon. I think I was doing mu first and phi second, but immediately if you exercise afterwards, I will ask you to do a reverse. So it doesn't matter. And we're gonna talk about, like, say, so this of course involves a lot of sampling, and also later what we're gonna call diagnostics to see if this is working. Then you will see some other features about what you should do. For example, does the initial value matter? Because you might just pick random values from mu and phi, right? And later we're going to see that how to do diagnostics for that situation. So in short, what we're doing is the sequence of the parameters that we're going to generate, they may be viewed, but not necessarily yet, as dependent sample from the joint posterior distribution of mu. So in short, what this is doing, if you remember, our goal is the joint posterior. We want to get the joint posterior, which if we express it will be 1 through yn. Right? We want the joint posterior, but we don't know how to get it. We can derive it, but we don't know how to sample it because it's just going to be a whole thing together. It's going to be a likelihood times the prior from mu, and then from the times the prior from p. Okay? So we are giving, like we're using a technique, what we call Gibbs sampler, is that we can use method to approximate this joint distribution. But what we do is by the two full conditional posterior distribution, and we do it iteratively. Okay? So what we have, is mu given y 1 through yn, and then phi. That's the first one, full conditional posterior, and the other one is phi given y1 to yn and mu. Okay. So we have this two, and we can sample them iteratively through the Gibbs sampler, and we are hoping that the draws that we're going to get from this iteratively will be a good approximation to the joint distribution. So that's the goal. Okay? That's why we're doing this, and that's how this can be helpful when you're having a really big joint posterior distribution that is really hard to further either sample or even just summarize. You have no ways to do it. But we can break it into one parameter at a time from this full conditional posterior distribution. Okay. So that's why we want to work on this. And here, this is how you can do it, like step by step, something like an algorithm here. But notice that we're writing not necessarily yet. So that's where those MCMC diagnostics is going to come in. We have to make sure that it will be a good approximation to the joint posterior distribution. And also, notice what we use the term here. We use dependent sample. They're dependent because the current draw of either mu or phi depends on its previous draw. Okay? We're doing it iteratively. Okay? But at the end of the day, remember in previous two chapters, we talked about multi-color approximation. Those require independent draw. Okay, say like you generate a large number of normal draws or large number of beta or gamma, whichever you do, you are taking independent draws. So multi-color approximation works well because you need independent draws to do the approximation. And now, as you can see, it's not there yet, right? We have a bunch of dependent draws. So later you will also see how we can make dependent draws to be independent and only use the independent draws to summarize the final posterior distribution. So all of those are important topics. You might have heard it before, or you might be wondering what they're doing. So once we covered the actual code, say to do this particular Gibbs sampler, I'm going to show you more about MCMC diagnostics and then how we can make sure that we're doing the right thing. Okay? Keep those in mind. So to actually doing it, take your time going through this. So this is the function. Okay, so I don't know if you have the experience of writing a R function before, but pretty much you are wrapping a few lines of code into a function. So later you can just call the function to write it. Okay. So here we're calling it Gibbs normal. So this is a Gibbs sampler for the normal sampling model. Okay. And you see that you will need some input. I will give you the input description later. But when you're writing a Gibbs sampler, you will want the number of iterations that you're doing. Okay. And also a seed, so you can reproduce the results later. Okay, so see that immediately I set up the seed. Okay, using the number that I feed in later, seed. I use set seed function. So here, getting y bar, getting n, and this is the key. This is probably something new that you never saw. So we're gonna take a sequence of draws of mu and phi, right? And we want to save them. So what you can do is you can create a matrix only containing 0. Okay, so that's what this first input is about. And it's going to be a matrix of dimension s times 2. S is how many iterations I'm doing, and 2, of course, the first column is for mu, the other column is for phi. Okay, so you initialize a matrix here. And for this particular sample code, you can see that I initialize a initial value for phi. Okay, so that will be later what we're going to put into the input, but just keep in mind now we're only needing the initial value for phi, and we assign it to this phi. Okay, So once you have this started, you can write a for loop for each of the iteration for the Gibbs sampler. So what we do, we update mu1, which is the full conditional posterior distribution of mu, it's mean. Okay, that's from, if you remember, probably won't, equation 14. And then you can generate a new mu from this new normal distribution. Okay, so that's why you have mean to be mu1 and standard deviation to be sigma 1. So equation 14 is being used in those few lines to compute what you mean. We saw it before when we're just trying to figure out, well, mu is unknown, sigma is known, how we can get the posterior. So they're similar in a sense, exactly the same, I would say, the code in lab 2. Okay? But now it's a Gibbs sampler, you have to sample them dependent from each other. So you have to do equation 14. And then all of this here is equation 15. That's as soon as you have your, remember, as soon as you have your previously drawn mu s from this current iteration, I'm going to generate my phi, right? So that's why you see why we want to generate mu and save it here, because immediately we will have to use this to compute the two parameters in equation 15. So you do that, and then you generate a phi. So you get your mu, you get your phi, you save them into the para matrix that we initialized in the beginning, and then once you have done with the entire function, you'll be able to get an output. So this is where you write the output. I want para to be returned in my function. So then you can access this para, which should be a matrix of S times 2 dimension. And then I can extract the particular draws later, which one that I want, then I can go from there. Okay. So I'll give you time to digest this, of course. I just want to give you a brief overview of what this is doing. And what you do to run the Gibbs sampler, you see that we need the input to go into the function. So the input should be the list of the data. These are the yi's, right? Y1 through yn. And also, in this case, I think for Jorge's question earlier, we need the prior choices, mu0, sigma 0, alpha, and beta. Okay, I'm giving them all for now. And for phi initial value for phi, just start simple, just use 1. Okay, so you need all of the input to go in here. And of course, so this is the case that we're running the Gibbs sampler for 10,000 iterations. I'm setting the speed 1, 2, 3. Okay. So you need those to run the Gibbs sampler together with the function that you wrote before. And lastly, you can extract the draws of the mu and phi from the output. So pretty much we save this as output, right? You can put it in a data frame and name each of the column correctly, so later you can extract them more easily. So these are most of the, I guess, mechanics aspect of this. And just to show you, once you do that, you can plot the posterior draws of mu. Okay. So what we did is, if you remember, is the para post, that's the data matrix with the column names mu and phi. So I can just plot mu itself. And then I can also summarize, say I want a posterior 95% credible interval. I can do that as well using the quantile function like we did before. Okay, only focus on the column of mu, and that's what you do. Okay. Yes?
How do you choose which initial p value?
Yeah, so that's up in the air, and we're going to talk about it. So when we go to the MCMC diagnostics, you will see that if the Gibbs sampler is running correctly and also doing a good approximation, the initial value wouldn't matter. Okay, so that's why you see that I'm running this Gibbs sampler for such a long time. I'm running for 10,000 iterations because I want to get rid of the effect of the initial value. So for example, so this we're going to dive into a little bit more. But for Gibbs sampler, what we're trying to do, say for mu, is that suppose the posterior distribution. So if we're going to plot all of the draws of mu, so this is a density function, so you can see how it looks like. But if you plot based on iteration by iteration, let's say iteration on the x-axis, and value of mu on the y-axis, then maybe you start with something here, I don't know. And then you will do things like this, but then eventually we wanted to fully explore the actual posterior distribution of mu. Right? So when it's converged, what we use the term converged, we're going to talk about the definition later, then the initial value wouldn't matter. Right? That's why if you run it long enough, and later you're going to see what we call burning, that we're going to chop off the first 50%, for example. So this will be, at least, I would say, the first step that we'll do. Okay. But there are other things we have to pay attention to when we do the Gibbs samplers. I will talk about them later. But to answer Josh's question, in the end, the initial value shouldn't matter. Okay. Yeah. And to that end, I think you probably can be convinced that, well, whether I give the initial value for phi or mu, it doesn't matter either. I can start my Gibbs sampler starting from mu or starting from phi, whichever is fine. The initial value in the end wouldn't matter. So this is how you can summarize the posterior distributions of mu, and this is what you can do about phi. Okay, so that is the case that you access the column of phi from the parapost, and then you can also do a quantile function here. Okay. So these are the mechanics, the logistics, I would say, the step. So I'm just going to give you an exercise, 2 exercises to think about, and especially, I hope you brought your computer based on my email yesterday, that you can try things out. So on Moodle, you will have access to the slides, but there's also a markdown file that I posted, includes all of the R scripts that we use in this file. Okay, so I would say open the, download, open the R markdown. You might just create a new R markdown or just empty script that you can try out these 2 exercises. Okay. So maybe not directly editing the R markdown because you might want to save it later, but you can always start a new file, either markdown or just a regular script, that you can try out these 2 exercises. So this will be the time that you have to dive into the script that I shared with you just now, like so many lines in terms of the function, how to write the Gibbs normal function, and also how to fit in those input values and then how to extract them. And I think we're just gonna, the rest of today's class, probably we're just gonna use the time for these 2 exercises to give yourself enough time to understand how Gibbs sampler works and how to actually implement them by yourself. Really quick, Julie asked a question about what set seed is doing. So this is trying to set a seed for the random number generator. So you will see that we fit that into one of the input of the function. So you always change this. The reason that you want to keep, say, a fixed number, just because later you might want to get the exact results, and then setting the seed will help you to do that. But it's not necessary. And I would say the beauty of Bayesian inference is that there's always this variability. You start with a different seed, you're going to get a different set of numbers. Those numbers will be very close to each other. Okay? Yeah, a quick comment. So some of you might download the R markdown file and try to knit it. You might run into not being able to do it because, well, it requires the JAX code, or JAX software, which we'll try to install next class on Thursday. So for now, maybe just focus on the part of the script that is relevant to what you're doing right now, copy it into a different R script, and then work from there. So it just, when you try to knit it, it's not going to work because we still have to download another thing. But that's not relevant to what we're doing now. It's for later on Thursday. Yeah, so don't worry about it. All right, so focus on exercise 1. If you look at the script, I don't think I will be able to type it to show you in action, but we can look at the code together just to discuss where you should be changing. Okay? So this function, the function that I provided on the slide, I think this is the case that you're going to start with speech, and you're going to update mu first, right? So what you're going to do is you're going to change this line to, I think if you call it, we can call it mu, and then you do input, $, and mu in it, okay? This will also relates to later how you're going to change the input, okay? But in the function, this is the first thing that you should change. And the next step, I think, is you will have to move this few lines. Before the previous ones. So bring it over here. Because now if we're going to start the Gibbs sampler using mu in it, that means we should update our phi first. Okay, so the 3 lines in the box, in the red box here, those are the ones that you need to use to update phi. So you should bring it up. And then the remaining 4 lines, I think, will just stay there, like after the box. But then the final thing here still stays, because you should save both mu and phi, the one that you drew, into the para matrix that you're going to use later. Right? So this will be the first thing to change. And then the second thing is when you are trying to run the Gibbs sampler, you have to change this. Okay? Because now we're doing mu in it. And you can start with any number, like 5, 10, whichever is fine. Later you will see that if you run it long enough, it doesn't matter what the initial value is. Okay, so this is my hint to all of you. And for the one last minute of class today, just want to show you how to extend it to more than 2 parameters. So sometimes, so what we're doing right now is 2 parameters, right? Mu and phi. But sometimes the model is going to contain more than 2. And what you're going to do is, first of all, you have to derive each of the full conditional posterior distribution. Okay, say so here I'm using theta 1, theta 2 to theta m to represent the m different parameters in the model. Okay, so what you do is you should first derive the full conditional posterior distribution for each of them. So you're going to have m distributions. And then you can go to your Gibbs sampler. So for the first parameter, what you do is you draw it from its full conditional posterior distribution, right? So suppose I'm working with s plus 1 iteration, then my theta 1 should be depending on all of the previous iteration values of the other parameters, right? And then when I go to my theta 2 s plus 1, then because I just drew my theta 1 s plus 1, but then the other was still from previous iteration, so I have to make sure that I fit in the new value. And that's what we did before, just now, with the 2 parameter case. You do that for theta 3, you do that for theta m, and then in the end, after this iteration, you have a set of m parameter balls. Okay, so imagine if you're going to do it in a function, you just have to have different chunks, right? Earlier, we had the chunks where we have, the chunks of dealing with, so this is the chunk about mu, this is the chunk about phi, right? So imagine now you have a chunk for theta 1, chunk for theta 2, until a chunk for theta m, and you do it all in a big group. Okay, so that's how you're going to extend it to a multiple parameter model. Okay. All right, we're going to end here, and Thursday we're going to continue the discussion, and yeah.